online, so I will not use slides from a PowerPoint presentation. I will just sort through some operational home pages and show a little bit how our experiment has been evolved in the years. So I start with some with the HEPEX page, with a blog that Florian started on May 30, where he tries to look which HEPS systems are available around the globe, and he compiled together with other contributors a list of systems at the European scale, at the global scale, for different countries: Italy, the UK, also experience from Bangladesh and France, United States, and France, so Finland, Sweden, and in the end, or at some point, gave also the contribution about Switzerland. We have two kinds of operational systems in Switzerland. There is the main one, which is operated from the Swiss Federal Office for Environment, and they are making ensemble forecasts since 5 years with use of the FUSE system connected to a HPV model and also to other hydrological models. And the other chains which are run operationally are operated by my research team at WSL. And on the blog in the table there is a link, and this is the place where this presentation will continue. This is the start page of our team's operational page. It summarizes a little bit all projects of our group since 1994, well, since 2003, it was the history before, and until this year. So each year I had 1 year, and at some point I had also project which has a particular interest concerning operational hydrology. And on the front page, you can also see an operational simulation of our system for a small river in Switzerland. This is today forecast with a model which gives results for the next 24 hours, and what we present here is a time-lag ensemble which has some kind of jumpiness. Today forecast is maybe not very interesting, so in parallel I always put also some examples of past forecasts where something was going on. This is an example on May 31st, 2010. So we jump now a little bit within the projects, and we start with the model, because any operational application has some model in background, and models have been developed over the many years. So the model we are using is the Preva modeling system. Its development has been started in 1994, and in 2003 we were so far that we decided that the model is useful for operational applications, and we invited in 2005 some stakeholders in Switzerland, about 100 people were represented, and I translate now: hydrological watershed modeling, results, and potential for application in practice. This May 2005 was also some months before a very large flood in Switzerland, which occurred between the 20th and 21st of August. And from this point on, we really started the operational research with first deterministic application and later on with operational application. In this kind of presentation that I'm now making, in some years there is no slide. There are some also links to the principal publication that we make on these topics. It's maybe funny, but our first operational application was not for Switzerland, but it has been for a watershed in China. This is a project we had together with another company which was focused on remote sensing. I was there in February 2004 in Yichang, which is downstream from the Three Gorges Dam, and this is a situation with low flow, with a runoff of about 4,000 cubic meters per second, which is the highest flood ever recorded in Switzerland. And the peak flow on the same place can be about 60,000 cubic meters per second. For instance, such an example was in September 2004. Close to this section, there is also a building, and on this building there are also marks for every major flood in the last 200 years. And This point here is about 4 meters higher than this water level where already 60,000 cubic meters per second were recorded. So it can be worse. So our task there was to provide some operational estimation of the inflows to the Three Gorges Dam. The Three Gorges Dam is located here in the downstream part. In the upstream part, there are observations in Chongqing, and another river on the side is also gauged, but this whole area was not gauged. And we were able to calibrate a system and set up a system, and we made some training with the Chinese people on site, and we developed a system which was connected to their operational database, provided the data of the last days that were processed. We subdivided this region in 31 sub-basins and provided in operational mode simulation for the next 3 days as driven by the work model which was prepared there by a group of German people. On this project, we also had some experience in calibrating in ungauged areas, and this also led to a publication in Physics and Chemistry of the Earth. With this experience, we went back to Switzerland. Also started in 2004, and I will translate this. The situation of operational forecasting in Switzerland was the following. We had the Swiss administration, which was responsible for flood forecasting for the region below the major lakes. So the lake of Thun, the lake of Lucerne, the lake of Zurich, and the Bodensee, so the lake of Constance. In these places where we have this black signature, there were operational forecasts since maybe the late 80s for the next 2 to 3 days with a deterministic model based on HPV. Over the years, there was a growing need of forecast also for the headwaters, so these red sections, and we thought in 2004 that it would be useful to start research in operational forecasting for these headwater basins, which are not so prone to large-scale floods, but are also very fleshy and also affected by thunderstorms. So it is a very challenging environment because it's also very mountainous and with very shallow soil. So starting from 2005, we had the first operational application, which was based on the combination of real-time data from different sources, so Metro Swiss, the Federal Office of Environment, and also the Swiss Federal Office of Avalanche Warning. From the avalanche warning, we had the basic database because they were already making forecasts of snow for high alpine regions, and we could access this data, create a database for hydrological modeling, and then display data online on a web browser. In parallel, end users were able to download some data and perform scenario simulation on site and take decision in real time. This was the state before we started to go and start with ensemble prediction. And ensemble prediction started in 2007 and followed a workshop held in Bern of the Rhine Commission, where we presented 2 ongoing projects. There were the Map Decade Initiative and the COST731 Action. It was also the first occasion where I met Jutta Thielen, and I guess also Florian was at this workshop and presented IFKIS. So following this workshop, we presented our goal for 2007, and the goal was to implement an operational hydrological ensemble prediction system, gathering data from Metro Swiss, from a German institute, from the location where the stakeholders were, from the Ticino area in southern Switzerland, from the Federal Office of Environment. All this data conflued at WSL. We also collected data from operational gauge station, but also from weather radar. With this information, we created initial conditions for the forecast, which at that time were made at the ETH by Simon Yaun. Simon also got weather forecasts for different lead times for deterministic model and from probabilistic model. The probabilistic model is COSMO-LAB. With Cosmo 2, we had 8 forecasts per day for 24 hours. Cosmo 7, 2 to 3 forecasts per day over 72 hours. And Cosmo Labs, it was 60 members every day for the next 5 days. So at that time, the data processing was very complicated because we sent our initial condition to our FTP server, which was then accessed from ETH. And then at ETH, there were some computation, and then they produced figures which were posted on a visualization platform, and other information was put in an archive, which then was used for the evaluation of this ensemble prediction system. In 2008, we published this experience in Atmospheric Science Letter, and in 2009, we made a first verification of this experience, combining all forecasts that we had for the years 2007 and 2008. And what you see here is how the reference run is similar to the observation. And in red, you see the spread of the forecast at different lead times, few spread for 24 hours, and in growing spread for lead time going up to 5 days. Again, very slow spread in 24 hours for day 2, day 3, day 4, and day 5. So at that time, we were able to operate about 15 basins in real time, and we did it until 2011. In 2011, we had a major crash in our system, so we ran out of quota, and many experiments were difficult to recover. So at this point, it was the first time where we were thinking about giving up or continuing, and we decided to stay and continue our operational forecast as a small research team and gather more data, but we reduced the number of operational applications. And also this was followed by some papers. The COST731 Action was the second cornerstone. It was also started in 2006. And from 2007, we were possibly the first team worldwide which was able to present operational ensemble forecast and ensemble prediction where the hydrological model is combined with probabilistic weather radar. This was originating from our collaboration with Gus German from Meteo Swiss. So for a basin in northern of Ticino, so the southern part of Switzerland, but the north part of this region, he was able to generate from rain gauges and from radar a rain map from the weather radar quantitative precipitation estimation, and with some complicated algorithms, he generated also a spatially and temporally consistent ensemble of 25 members. And since then, we are able to generate this kind of plots updated every hour. They have no lead time, so the lead time is 0 because we work with observation up until a certain point, and then we continue then for the next couple of days, driven by numerical weather forecast. So the spread here is given by the spread of the weather radar ensemble, and this is done for the recent past. So it's operational hindtest, what we are showing. So these data have been also analyzed, and we were able to show that the radar ensemble at a added value as compared to deterministic radar products, and also as for very small basin, higher quality than as if we use rain gauges as an input. This is what I can say about D-phase in COST731. Again, this was always to start with operational forecasting. My institution is not only a research institution, we have also a goal that we disseminate our know-how to practitioners, and since 2009 we also deliver our forecast to a platform of Switzerland which is dedicated to information on natural hazards. It's the common information platform of natural hazards in Switzerland, and this is displayed in a also protected environment where all persons in Switzerland which have some task in flood mitigation can access and then have a look at the forecast. We upload there up to today about 20 basins in real time, many at different time of the day each day. So we have a kind of 365 and 24-hour operational service which we maintain in the team that I'm leading. And as a final goal, it was that we can combine our modeling system to the environment of the federal office, which is responsible for the operational warning at the Swiss scale. And to do this, we had to nudge our operational model to the FUSE system. Our operational national service uses FUSE since now 7-8 years. And we had a project together with them in order to create an adapter that our model can nudge to the informatics system of the federal office and then generate forecasts in real time also at another place than our group. So we made really also the last step of model development. We were able to deploy it to a end user which is then in charge for real-time operations. This was not the finish. We were then lucky to be included in the IMPRINTS project. It is an EU project which started in 2008, so early 2009. In 2008 it was the proposal, and there we will be able to collaborate with GRC, University of Catalonia, with different stakeholders, also University of Lancaster were on board. This project was not focused on some prediction for long lead times. It was focused on debris flows and flash floods, so we were interested on short lead times. So for this project, we've also developed some particular visualization. This is now a product which we started in IMPRINTS. It is a 5-day forecast for the Linz Basin, which is in the Canton of Glarus. It is a basin where there is some hydropower management, and we try to consider this by use of simple approximation. And this is then the 5-day forecast with some reduced turbination on the weekend and some possible higher discharge between Monday and Tuesday next week. And this is also in the frame of IMPRINTS. This is the forecast for the next 3 days for the basin of the Verzasca, and it is possible that we, in the night to Sunday, will have a peak flow of about 150 cubic meters per second. This is something which happens maybe 3 to 5 times per year. So if you have some time next week, you can go to the link that I showed before on the HEPEX page and control if this event occurred or not. So this is the fun of making hydrological operational forecasting also for research. You can verify your prediction some days later and not as for climate impact studies that you have to wait your son or grandson that makes the verification for you. The last work that we did in the frame of IMPRINTS, it was again a combination of our expertise with the expertise of MeteoSwiss. They generated a new product called NORA, it is a product which uses past radar fields for the generation of short-term forecasts based on weather radar. So it is an analog-based system, and we connected this with our operational simulation, and then we used here for the next hours this combined radar forecast with a deterministic numerical weather prediction model. So the spread is given by the forecast of the radar, which has 8 members, while the single lines are taken as taking the pluviometer data and the numerical weather prediction without radar forecast. In the second example, so we are switching between 2 case studies. The first one, we saw that the start of the event was possible to be forecasted by using this radar rainfall forecast, this first part. And in the second part, we see that also with using the radar rainfall forecast, we were able to anticipate the first peak. And if we were using only pluviometer and numerical weather prediction model, we wait a little bit that it is. So if we use no radar information, we miss the first peak. And if we use the radar forecast, we can anticipate the first peak with a lead time of approximately 6 to 10 hours. This chain has been evaluated. We had a publication in a special issue in hydrological processes in January, and a paper will also appear in Hydrology and Health System Science in the next weeks. So this was our contribution on flash flood with operational system. A new focus that we have since 2009 is also early prediction of hydrological droughts. So once we had some first success with floods, we had some requests from the practitioners about early prediction of droughts. There was a large suite project financed by a national research program, NWP61. It will be concluded in these weeks. The group was a joint project of ETH, ourselves, the University of Freiburg, and the University of Zurich. Our goal, we had a work package on operational hydrological modeling, was to assess the potential of snow water equivalent estimation for the early recognition of hydrological drought, but also to deliver operational drought forecast by combining meteorological data in real time with COSMOLabs reforecast, and also the VAREPS forecast issued by ECMWF. So our goal is to have until day 0 observed meteorology, and then for day up to 5 COSMOLabs forecast, and then VAREPS up to day 30. And for longer lead times, to also use the observed climatology, going from the current initial condition in order to see potential deviation from climatology and going from the current initial conditions. So this is the product we can provide in real time. This is a forecast for a period in October 2011, where we had a kind of deviation from climatology. So the horizontal line will be the median of the climatology according to the model. This is the initial condition some days before the forecast, and this is the simulation up to the day where we started the forecast, and for the next 5 days. So we were able to say we will have in the next 5 days something that in the climatology of the basin was observed in less than 2.5% of the time. So an indication of large deficit. So this is the water resources. This is no deficit. This is surplus, and the red lines are deficit. We can see here an animation for a longer period of forecast. This was a period in May May 2011, where we had a large deficit in water resources in a Swiss basin. So when this is no deficit, we had up to 50 millimeter deficit, and this deficit started growing in March. And here we see that in some days there could be some relief, but no relief occurred, so the situation got worse and worse, and at some point it was below the long-term climatology. And with this kind of comparison between long-term climatology and current forecast, we want to give some indication to the end user concerning hydrological droughts. And this is the forecast for the world period between March and November 2011, where we had this large deficit in May concerning soil moisture in the soil in our model, so far from the expected value. Then in July there was a rapid recovery, and a second drought spell was in late autumn. But at this time in year, this is less a problem because there are really enough resources of water in the basin. And this is the same plot for the total resources in the system, including also snow. And we can see here that there was already a deficit in March. In March, where not enough snow was, so it was a snow poor winter, and this poorness of snow propagated also in the summer. So this is the reason why we want to focus in the next weeks and months on anticipating low flow prediction by considering the snowpack situation in winter. Since this year, we have now also an operational platform where we give some indication about early indication about hydrological droughts. About this, I already had a blog on the HEPEX homepage, and here I can show you a translated version of this. This is the situation for today. This is really a live situation. We show a map which sum up all situations concerning critical situation for forests, for rivers, or for snow resources, or for soil moisture, and we give also a comment every day about the situation. And we have also some news about drought situation around the world, or also drought situation in Switzerland, or some general information about new legislation about drought in Switzerland. The current drought situation, I need to log in, so it's a password protected. A password protected environment. We have so far 180 users, some of them also stemming from the HEPEX community. We have a general situation, and we have a general situation concerning discharge, and some regional divisions, and some products showing in which gorges of Switzerland there is some possible deviation from the seasonal average. For instance, in this alpine area, we have now a situation of runoff which is below the 15% percentile, which is the first threshold that we consider for giving some early warning concerning hydrological droughts. All in all, the situation in Switzerland is positive. There are very few gorges where we have some early drought indications. We also plot the duration. How many days are we below this 50% percentile? We have here a couple of gorges with some days of where the runoff is persistently below this threshold, and we also give information about runoff deficit during this drought spell and magnitude of droughts during the drought spell. Another way to show a potential drought situation is the current precipitation over the last 5 days, and this compared to climatology. So we see that in this region of Switzerland there have been some precipitation in the last days, and therefore no deficit is here. And in some regions there was no precipitation, which is quite normal over 5 days for this season. For the 10-day accumulation, we see that in Switzerland there was in the last 10 days enough precipitation in the northern part and almost no precipitation in the southern parts. So let's go there for the weekend. On this side, we see that in most of the regions we have something close to the average of the climatology, so no particular deficit. And if we sum up over 20 days, we see almost no region is showing deficit. Here we give some warning if we have over 20 days less than 10% of the climatological mean over a specific region. So if in this region we will have over the next days no precipitation, at some point this region will be colored in light brown and later on in dark brown to indicate some precipitation deficit. The soil moisture simulation map is based on operational hydrological simulation, and we provide a pixel map at 600-meter resolution about the field capacity in our model, and also here we have some thresholds in order to give then a general assessment for the regions. Groundwater, we still don't have any operational product, but it's scheduled for next year. About snow, we have a product showing snow deficit in alpine areas, but it's only active between November and May. So at this time, no operational product. This is the last map that it was issued last June, showing many regions with some abundance of snow. So it was quite snow-rich winter last winter, and this is also the water that sustained then the low flows in summer, so that mostly in the valleys region we had during summer almost no risk of hydrological drought. A further product is drought in forest. This operational map is based on the so-called Nesterov index. The Nesterov index is something which is generally used for fire warning, but we use this as indicator of dryness in forest. And we see here in the regions where there has been no precipitation over the last days, there is also some indication that forests might be drying. So we had constantly about 20 degrees temperature over the last 5 days, and the earth and the leaves of the trees and also some parts of the regions below the leaves might be drying. So there is more risk that if you go there and make a fire, there could be some propagation of fire if you lose the control on the fire. And a last product we show are water temperatures. This is important for fishery. This is the current situation of water temperature. If the temperature is about 24 degrees, then some trout species might be killed along the rivers. So we give also information about this, and also because we have still some atomic power plants along the major rivers, and they should avoid to give to the river the water back which is higher than 24 degrees. So with this product we can also inform authorities, but also fishery authorities about some danger for fishes along the rivers. So I go back to the main presentation, and I come now to our main products that we make since some years, and tell me if I'm going too too long, the main project that we have is the operational simulation for the railway station of Zurich. This is the Alp River. For this river, we plot the we have seen at the beginning of my presentation this time lag forecast. This river has an artificial dam which separates this upper part of the river to the lower part. The turbinated water is going to the Lake of Zurich, and these two basins are quite prone to flash floods. So if you can have a strong thunderstorm which can cause here discharge of about 300 cubic meter per second up to Zurich. And this basin has an area of only 350 square kilometers. It looks nice, but it can be dangerous because if the dam overspills, there can be a superposition of the two flood peaks until Zurich. Some years ago, there was this river section where the maximal flow is about 350 cubic meters per second. It has been reduced by 60%. So 60% of the river section was closed for about 3 years. And during this period of time, we established our operational system, and we make a real-time forecast based on ECMWF, in which Cosmolabs is nested, and then we feed our hydrological model, and we combine this with the hydraulic model, which also includes the water balance of the lake, and then we give our forecast to the end users. I wait for something. This is a paper, and this is a situation where there was a historical flood in Zurich, and this is a situation which does have to occur in the near future. Last May, we had an event which brought about under 80 cubic meter per second, and during this event, we made a backup of our forecast system, which is now loading. So this was our forecast issued on the 30th of May. So sorry, it is loading now. Still waiting. I have to close some. So this was the operational forecast given on Friday 31st May for the next 5 days. We had some probability to reach peak up to 350 cubic meter per second. The median of the peak would have been expected for Saturday early afternoon, and the expected maximum peak is expected to be about 150 cubic meter per second. The deterministic model, also this one, I go a couple of forecasts back, and I hope that it will load quite quickly. So this was the deterministic forecast, also giving a peak of about 150 cubic meter per second. But here you see the jumpiness of the forecast. So the last forecast is always the darkest one, and the earliest forecast is the shortest one, and the one with the less intense coloring. So with this information, it has been quite difficult to give some indication to the end user, but in the end, it has been decided to make an artificial drawdown of the lake to increase the capacity of buffering the peak by the lake. This is not a real hydrograph. It has been decided to release water from the lake over a time of 12 hours to increase the storage capacity in the lake and then reduce the peak in Zurich. I could talk hours about this experiment and about this particular forecast. I can give you additional information if you will request this later on. So, and you were asking how many people maybe are involved in this. So we are a team of about 10 people, but 2 of them are master students. We have a trainee, 1 PhD student, a couple of scientific staff members, but all of them are working on climate impact modeling and not on operational forecasting. So it's a large amount of work on few people to maintain this 365 24-hour service for research and for practitioners, but we have really fun on this, so we will continue even if we have work also on Saturdays, Sundays, and in the night. So this was my contribution to this HEPEX webinar. The next one will be given on October 24 by Anders Persson. Is the second part of a well-received webinar which has been held a couple of months ago. And with this, I give the word back to the moderator, Ms. Anna Gelli.
Yeah, sort of. Thank you very much, Massimiliano, for the interesting seminar. Any questions from anybody? You have to unmute yourself if you have a question first. Oh, Elias, I've unmuted you. You should be able to speak now.
Yeah, can you hear me well?
Perfect.
Okay. Massimiliano, thank you very much. I really enjoyed this presentation. I do have 2 questions, and I'll go straight to them. So the first one is if these forecasts are actually compared with the IFKIS forecast, and if there's any feedback towards IFKIS and also from IFKIS towards the forecast that you made.
So with IFKIS, we had some small qualitative comparison during the IMPRINTS project. We had during a couple of events, we were comparing for the Verzasca river and for other river of southern Switzerland. Jutta was showing me her forecast, and also Lorenzo was involved back then, and we were showing our forecast. Over the whole duration of IMPRINTS, our operational forecasts were accessible to all partners for the test areas that were covered by our simulation. There was no constant comparison, and in the end there was no study about comparison over 2 or 3 years. Our simulations are archived, so this can be done in the next times if there is some interest and some person having the capacity, the time to do that.
Yeah, I think that will provide a lot of information just to understand model inadequacies in some areas. And then the second question, if I saw some large lakes in the map that we have, is there any, do you get updates of the water levels at those lakes?
For the seal lake, we update the lake level every hour. So we reduce the uncertainty of the lake level by assimilating the lake level of the seal lake every hour. Yes. We have no operational information about how much water is turbinated and diverged to the Lake of Zurich.
Okay, thank you very much.
You're welcome, and cheers to Switzerland.
Yes, any other questions? Okay, there's no other questions. I'm sure you can also email Massimiliano if you have any further questions. Thanks again for Massimiliano for this presentation. Thank you very much.
Welcome.
You already announced our next presentation, which will be by Anders Persson again. who's given a exceedingly popular presentation with loads of clicks on YouTube already. I'm sure Massimiliano will also be very popular. Thank you very much, and I hope to see you next time again, and goodbye.
Bye-bye.